I'm Michael Mattern. I'm actually more of a guest researcher at CWA currently. So I'm at the moment basically hobby astronomer, which is also the reason why I will show you not too many results, more of a lot of work in progress. And work in progress means like some of this is actually just from last week. Yeah, be careful with some of the results I'm showing. There's like a lot of things that needs to be done, but I also want to present you more of the method, the ideas behind it, and maybe I find someone to collaborate with on this work. Yeah, so actually a lot of introduction was already done by Alvaro and by Philippe. I will talk again about ISM and structure in the ISM, and yeah, just looking at these nice Herschel maps, we see there's a lot of structures in there. There's a lot of going on. And all of this is shaped by gravity, turbulence, feedback from actually ongoing star formation. And what is then typically done is really just assuming some simple geometries like spheres or cylinders to get the idea of like how can we describe this in an analytical way. And we then categorize all of this into a lot of different structures. And as Alvaro pointed already out, like filaments, they somehow they span a large ranges of different size scales and so on. So there's not even a proper definition between all of this. So it doesn't even make sense to analyze specific structures at specific scales. What I've actually done during my master and continued in my PhD was analysis of the fragmentation of the Nessie filament, which you can see up here. So identified all of the clumps, derived separations and densities, and then compared this with exactly these models, the analytical models based on basic geometries. What we figured out, like the fragmentation is best in agreement with cylindrical fragmentation. And it also needs some component from turbulence, scale-dependent turbulence. What we did not include is any impact of the magnetic fields. And what we also see is like this is really clearly hierarchical. There's not much of a change in between. So one could think, okay, all of this is happening scale-free. Hierarchical fragmentation from the cloud scale down to dense cores. However, you also see like we're kind of limited here by resolution. Then Philippe mentioned already, like with the Herschel Gould Belt, there was a lot of studies of filaments, and what they found is like there's this characteristic width of 0.1 parsec, and that kind of points out, okay, there might be some characteristic scale that we could not see up here. But the question is, how can we actually identify what is going on? And now looking at scales, so what Herschel can observe is like down from somewhere around like 18 arc seconds if you do the best methods. And then like scales, the high-gal tiles are typically around 1 square degree. Yeah, but Nessie is already like at 3 kiloparsecs, so this is not feasible to observe within the Gould Belt, like up to 0.5 parsec. You barely resolve all of these things. So clearly there needs to be something done here. Now, the first approach for which I actually came originally to Paris was to work on the caffeine survey, which used the ArTeMiS receiver, which is actually still at Apex, just not working currently. And here we get continuum observations at 8 and 10 arc second resolution. And we then can combine those with the Herschel maps, typically the high-gal because it's galactic plane. And then we compute column density maps, which then includes all of the different scales from 8 arc seconds up to all of the Herschel parts. So we actually gain a factor of about 2 in the resolution. All of this data is, or most of this data is publicly available on the ESO archive by now. Also, an advantage is we can correct for saturation effects that you see in the Herschel data. But obviously, this is still not enough of resolution. So then James Webb came around, and we were like, okay, what can we do with James Webb? It's observing in the mid-infrared, and in the mid-infrared, these star-forming clouds are typically dark. So why not use James Webb to map infrared dark filaments? Philippe showed already the NGC 6334M, which is sitting like here in this very active star-forming region. So you have a very bright background, a local background, which gives some complications of like varying background intensities, make things a bit more tricky. Then within the same larger complex, we also observed the NGC 6334N, sitting in a more remote area, which makes the analysis somewhat easier, but also it's less dense. So with less background intensity, you can observe only like less density. We then also included some more filaments at different distances because we wanted to see what changes with resolution, with physical resolution. And you see if we then use James Webb, and actually this image here is from the Spitzer glimpse survey. So now we actually can access this area of resolution. Okay, so when in absorption measurements, so we have the infrared background, which is typically some very diffuse galactic emission. So towards the center, it's typically a bit better than if you go the outskirts of the Milky Way. And then you have some structure in between that is absorbing this mid-infrared intensity, and we have what we observe. Now, obviously, to get an idea of the density, you need to, first of all, know what is the foreground intensity, which the common approach is to really just look at what is the darkest point and assume this is basically all of the emission that's coming in front. But then we also need some idea of the background. And for the background, typical approach was just filtering the whole structure. So like Butler and Tannis is an example for that. However, if you look at only the James Webb data, you see the field of view is actually quite small. So you cannot use a big filter to get rid of all of the absorbed material. So the next approach was to combine or to make an inlay basically of the James Webb data into the larger Spitzer data. And you can see that there's like the diffuse extended absorption is way larger than what we actually observe here. And then, yeah, we still were like, okay, we do actually have some idea of the column density of this data, which, this is right. So, which we actually have from caffeine. So here we have the caffeine data, 8 arcsecond resolution. So we have a nice column density map. You can also see that all of this bright emission here is actually not that dense gas, so that's a bit problematic in all of the analysis. But we get an idea of the low resolution column density, which we then can put in and then derive some of the background from this. As I said, we only can measure absorption once our observation is actually the intensity is lower than the background, so which means everything that's bright in the mid-infrared is problematic. And this is especially all of these stars in here. This will cause some issues. So my first approach is basically just masking them and trying to interpolate from the surrounding area. However, it still leaves several artifacts, especially if you have some bright sources in here. You see the PSF afterwards. You also have in the Spitzer data some artifacts up here, and you still like the removing stars in Spitzer is a bit more tricky. So I'm also working on using a neural network to train to remove stars. However, to do this, I will need to create some mock data to train actually the neural network properly. So this is something I'm still working on, and I did not finish in time to show you anything of it. So now deriving the background. So I basically used the equation that I showed you before and built a small tool. So to just understand what is actually going on. So you have the column density from the caffeine data here. You have the smooth intensity from the mid-infrared. That's the distribution of the whole field. And then whatever is in this box is in here. And then I basically just fit and get an idea of, okay, what is the foreground and the background for this field. And if we do this like over the whole area, then we actually get a full map of the foreground variations and the background variations, which we then can use to derive the column densities, assuming that they are not changing too much from this arc-second scale to the James Webb scale of 0.3 arc-seconds. In principle, we can also play around with opacity, different approaches, but yeah, I will not go into this one. Okay, and this is then basically results that Philippe kind of showed already. So this is already published. We have the Herschel apex, the caffeine column density. Here we have what we get from Spitzer alone. And now this is our new method from caffeine. That's and this is just the intensity map from James Webb with the Spitzer around it. So you see all of the improvement that we get. Also, you see the beam, how it changes to actually not being visible here. So now we have this nice column density map, and we want to understand, like, is there some characteristic scale? So to understand whether there's a characteristic, like something changing in between, whether there's a break in the hierarchy, in the hierarchical cascade, we do a power spectrum, and we do this on the James Webb data, which you can see here in red, and we can also do it from the Herschel data, which you can see in blue. And then if you fit those, you can see there's some kind of a breakpoint. You can see here the fit of the slopes, and the breakpoint is around this, well, 0.1 to 0.4 parsecs, so it's slightly above the 0.1 parsec, but there is kind of a break. Unfortunately, the break is directly where the two data sets are, kind of barely overlapping. So it's not, it's an interesting result, but it's not maybe really robust because there could be something wrong with the calibration. So that's now what we did last week. We looked into some of the other structures. So here, this is G34 with James Webb. We observed a region down here and actually another one up here. In between, there's some heavy star formation going on, so we won't see any absorption. So we did not use. Oh, okay, the plot is not showing. No, it's down here. What happened? There must have been some problem in the export. Well, yeah, in principle, it looks. I did not see this. I'm sorry. So in principle, it looks not too different from this one. Just the breakpoint is at a somewhat larger, it's somewhat larger frequency, so it's more distance, which means it's around the same physical scales. However, there's again, like the fitting is not very clear. So I'm afraid it probably will be the same here. Yes. So we have another one which is at 5 kiloparsec, which is G53. Here you actually could see a really nice overlap of the data, and there's the breakpoint, which is again around this 0.1 to 0.3 parsec. So there seems to be some characteristic scale in all of this. Yeah, it's a bit unfortunate now. Okay, now going back to what Philippe was already showing, so we also measured the width in NGC 6334M, and this is like this conversion, so like with higher resolution. So you see all of those blue data points; they are coming from this paper, and you see it's kind of leveling off at a specific width, which is around 0.13 parsec. We also use different methods. They all kind of go to this 0.12, 0.13 parsec. So they're all kind of in agreement, which is an interesting find. It shows there's a robust measurement of the width. However, what is always important if you look at filaments and the width of filaments is to show from where do you actually measure. So here's the spine, and this one was that was used for these measurements, and this one is actually from the Herschel or caffeine similar data, because it's technically not part of caffeine. So it's actually a relatively low resolution spine. That's also something I was working on last week, but I could not continue, is actually to identify all of those substructures that we find in those images. So we have a very high resolution, so we can break down this larger filament into all of those fiber substructures and basically do similar to what Alvaro did on the molecular line data, also in the continuum with these. However, what we are missing is the velocity component, but we are not limited by any chemical compositions or excitation problems. So I think this is a very complementary approach. Like ideally, one would want to have those absorption measurements to get the continuum at high resolution, and then on top of it, the high resolution velocities, and then see how all of this combines to see how gas is flowing, how where do we form the cores? Is it like in the junctions of those fibers? Is it in the center of fibers? Is there fragmentation going on? So I think this is something that we need to do and like understand the full spectrum of scales from continuum and from line observations. Then one question remains: if we have this characteristic scale, it's like why? There's a few good guesses. One is like the change from the supersonic to subsonic velocity ranges. But Philippe mentioned already, and because Dasai is also here, I also wanted to show this. Like Dasai has this nice tool or nice process that he's simulating, which is called STORM, and I will not try to spell out all of this. Highly encourage you to talk to him about this. But what we find in this NGC 6334 study is that so here we have this main filament, and in the diffuse parts towards the sides, we find all of those striations, these small-scale filamentary structures. And if we now measure the frequencies across those and compare this with those kind of finger structures that he sees in his simulations, we do get some kind of comparable frequency spectrum for this structure. So there's something interesting in here, and I think this deserves more investigation. Then we have the summary. So, I showed you the caffeine. We have this nice data set, so you are very welcome to check all of the data out. There's a lot of different clouds. I showed you all of the process. I will not repeat this now. And if someone has any ideas on improving the removal of stars and like how to analyze structures, filaments on different scales, you're very welcome to talk to me. Thank you.
Any questions?
Thanks for the talk. It's really unfortunate that those figures didn't show up. So where you showed the beam area, I was just wondering sort of how many beams, so how confident are you that it isn't that? Because it just seemed you've got kind of, on one side you've got the resolution and on the other side it's kind of a sampling.
So you mean...
yeah.
You mean here?
Yeah.
These areas? So yeah, the beam size is typically just below here. There's some beam correction also done here. So in the other plots, I was actually planning on showing them. So here you actually have like the beam limits kind of shown. Yeah. There definitely is some area in here where it's, yeah, it's exactly where noise and
I don't know whether it's
with the small scales from Herschel. So I guess you need data that has some overlap to give you some validity to this. That's the whole, like that's why we're trying to combine all of these different scales to cover everything.
I understand that. I just wondered on the larger scales where you have the overlap, if it's a sampling issue. enlarging. So you get limited by your map, basically.
Yeah.
So
yes, but should put out, we should point out that the power spectrum derived from the Herschel data comes from a much broader, much wider field of view. Square degrees.
Yeah.
So it's not just this small.
So this.
Thanks.
Yeah. Yeah, that's something I forgot. So yeah, that's actually was also on one of the slides I didn't show. Sorry.
Any other questions?
To me, it seems that you see more structure in 8 micron that you lose when you mix with Herschel. So have you tried to look at what is smallest size you can detect in 8 micron? Only Spitzer or only James Webb without forcing the column density with Herschel? Because maybe the Herschel data is useful, but it brings also information at low angular resolution that finally converge to 0.1 parsecs. So I'm not so convinced that if you use only absorption, you find this.
Yeah, in principle, yes, we should also do it on the data, on the intensity data directly. Not sure whether you did some tests on it. Yeah. So the problem on these maps is always that, like, showing them on screen, you always lose a bit of depth. But the small striations, you have a sense that they are in here. So they're not really coming from Herschel because Herschel cannot see them. They're way too small. So these striations do come from the 8 micron, and we do see them still in the column density map. What? Yes. Yeah, exactly. Here, this fiber, for example, this also has been detected with ALMA, so that we have some ALMA data for this one as well. It means, like, if you do like this, measuring the width and measuring things, you always need to keep in mind from which scale is your spine coming from. So there definitely is substructure there. That's out of the question. This is not. It's just. It might not be a fully scale-free cascade. There might be some scale in between. That's all we're trying to point out here.
I think there is one last question on Zoom. Go ahead.
Hi, Marco.
Yes, we can hear you.
So we don't hear you, Ashley. Your question is about measuring the width of the filaments using near mini-infraring extinction versus dust emission suffer from the same problems than using different gas tracers, N2H plus versus CO, in view of the absorption of the saturation or saturation problems.
Well, saturation problem definitely can be an issue, but so this is the profile here in green is the intensity profile. So it kind of fits what we see in column density as well. So it's kind of it's very similar. But yeah, there might be some differences which
You never see saturation of your absorption measurement?
Oh, they are in the center. There's definitely absorption going on. So we originally tried to find also some dense cores and so on, but we don't really see them because there's too much saturation going on. But if you average over a filament, then you have some absorbed locations there, but some saturated locations, but the whole spine is not saturated, which kind of gives you an idea.